Hi you guys, sorry my last video got interrupted there, but what we were talking about is that this 180 degrees, I just need to subtract that 36.16. Because this is the quadrant where sine is also positive, that's going to give me the second value that works for this sine term. So if I subtract that off, I can just plug that into my calculator. So here I'll do 180 minus 36.16. That gives me an angle value of 143.84. So that's going to be my second answer. That means I have two angles, both of whose sine is going to be 0.59. Now this is calculator based, so I can check my work. Here I'm going to take this sine of 36.16 degrees. Notice this is a decimal approximation, so it's always going to be a rounded value for what this is, but I get out 0.59 in my calculator. Then I do sine of 143.84, and I also get 0.59. So I got the two key values that I need. So that's how I work with inverse trigonometric functions when I'm in that circular reference frame. Let's try another one, and it's going to be the same kind of operation, but we need to pay attention to what's going on with our signs. And in this case, I mean SIGN, so our negative and positive signs, not our trigonometric signs. So here, this problem says, given that x is in between 0 and 360 degrees, so again, I know I'm working in degrees, identify where cosine of that angle is equal to negative 0.78. So, same kind of procedure as what I've seen before. If I have an angle whose cosine is equal to negative 0.78, then what I'm just going to need to do is to take the inverse of that value to find my angle. So I go into my calculator, inverse cosine, negative 0.78. And the value that I get out is 141.26 degrees. So I get 141.26 degrees. Now let's go ahead and graph that value. So I've got my XY plane. And if I'm working in a circular reference frame, that means that I go over here. That's my initial side. And my terminal side for 141 degrees is going to be over here. So that's this angle. It's 141.26 degrees. So notice, if we're thinking about values as we go around a unit circle or a circular reference frame, over here, all of my trig values are going to be positive. Over here, just the sine values are positive. Down here, tangent's positive, and over here, my cosine is positive. So what I want to think through then is, here and here, cosine values are positive. But what I've got going on here is that my cosine value is negative. So that means the two angles that have this cosine result are going to be in quadrants 2 and quadrant 3. Because those are the two places where cosine's negative. So that just means I need to figure out, okay, what's going to be the angle here? This will involve one more step than what we saw in the previous example, because we are working with reference angles. So it's really important to remember that we're not just working with the values of the angles themselves. We're working with the reference angles, which we talked about in our last section, are the values that get you to the closest x-axis. So here, I want to find my reference angle by subtracting 180 minus that 141.26. So when I do that, I get a reference angle of 38.74 degrees. So that's this angle value right here, is 38.74. Then I need to find my second angle, but I know I'm over in this quadrant here. So that just means I have an angle with a reference angle also of 38.74 degrees in this quadrant. So let's draw that out. This other angle is going to be here with a reference angle, meaning getting back to the x-axis, of 38.74 degrees. So if I want to get this angle measurement, I'm at 180 degrees and I go 38.74 more. So let's add that together. 180 plus 38.74 is going to give me an angle measurement of 218.74. So those are my two angle solutions. 218.74, 141.26 degrees. And again, we can check that work by plugging into our calculator. First up, I take the cosine of 141.26. I get negative 0.78. Again, I would have to round here, but that's because these are decimal approximations. Then I take the cosine of 218.74. And notice I get the same value. So you always want to check your work, because if you plug in the cosine or the sine or whatever angle value and you don't get this term that you started with, then you know that your work wasn't correct and you just want to go back and make sure your reference angle work was done accurately. Let's try another one. And after you see about 5 or 6 of these, they really become like second nature, the work that we're doing. Here, this says, given that x is in between 0 and 360 degrees, identify where the tangent of x is equal to 0.42. So that means I'm working in degrees and I'm going to have 2 solutions. So if my tangent of x is equal to 0.42, then the inverse tangent of 0.42 will give us the angle x that we're looking for. So we come on over to our calculator, inverse tangent, 0.42, and we get 22.78 degrees. That's our first solution. So then we just need to go to our circular reference frame and figure out what reference angles we're working with in which quadrant. So here, my angle value, I've got my initial side and my terminal side, and this angle is 22.78. It's really easy to figure out reference angles in the first quadrant because it's just your actual angle value is the degree measurement to get back to that axis. So going around the circle, all of them are positive there, sine's positive there, tangent's positive there, and cosine's positive there. Here, tangent's positive, so my first answer is in the first quadrant where tangent's positive. The other place where tangent's positive is down here in quadrant 3. So what that means is that if I'm at 180 degrees here, to get into this quadrant, I need to add this reference angle of 22.78. So this value of theta here needs to be 180 plus 22.78 degrees. So I go to my calculator, 180 plus 22.78. That gives me 202.78 degrees as my answer here. So I've got 2 angles, 22.78, 202.78 as well. Remember, all I'm doing here is I get one answer from my calculator, I identify the reference angle from that term, then I look for the other quadrant where that trigonometric function is either positive or negative depending on this answer. So I simply add that from whichever quadrant applies based off of the work. Once you get your 2 values, you want to come on back. Tangent of 22.78, that gives me 0.42 rounded as well. And then I go to tangent of 202.78. That also gives me the same value, so I know I'm good to go there. Now, a key piece of information that's useful to know about these kinds of problems is that they can either ask you for 2 solutions or they can ask you for both solutions. So, for instance, notice here we were told that our result needed to be between 0 and 360 degrees. So if I start at 0 and I go all the way around my circle, that was a really bad circle, but if I'm starting and going around, that means I encounter both this angle and this angle that have that same tangent result. I could also be given this problem with one of the 2 possible restrictions. One of the restrictions could have said that my angle needs to be in between 0 and 90, in which case I'm just looking at this quadrant. And if I'm only going from 0 to 90, the only angle that I encounter with that tangent is going to be 22.78. So if I had that restriction, I would just report that angle value. Alternatively, I could be given the value or the restriction that my angle needs to be in between 180 and 270, which would mean I'm over here in 180, going down to 270. The only angle I would encounter would be 202.78. So my recommendation would be not to necessarily consider the restriction right away, but to solve the problem the same way we just have, and then take a look and say, okay, am I being restricted into one quadrant? And if so, which angle value matches up? So that would be the work that I would do. So on your homework, if you notice that these angle values are a smaller range, either between 0 to 90 or 90 to 180 or whatever the situation may be, notice that your process is the same. You're just selecting the correct angle that applies. All right, you guys, so the first 3 examples that we did all involved degrees. So we're going to take a look at 3 examples that involve radians. And radians are ever so slightly strange when you're working with your calculator. The reason for that is we haven't done anything with radians aside from arc length and sector area, where we convert our radians into decimal forms. So what I want you to start off by doing is making a circular reference frame where you're working with radians. So remember, when we deal with our radian values, this over here is going to be 0. This up here is pi over 2. This is pi. And this is 3 pi over 2. Now, when it comes to calculator work, we're always going to be having decimal approximations. Pi over 2 is not a decimal approximation, so we need to make it win. If pi over 2 is our angle, we're going to use the approximation 1.57. So that's going to be this value here. Pi, we know, is 3.14. So that's going to be what we use here. 3 pi over 2. 3 pi divided by 2 is 4.71. And then if we were to call that 2 pi instead of 0 and we get all the way around, that would be 6.28. So everything we do in this section will involve decimal approximations of radians, not actual pi values of radians. Now, the reason we know we're working in radians when we look at a problem like this is it says you're in between 0 to 2 pi. So you need to report your answers back to radians. Now, remember, if you don't like to work in radians every single time, it's okay to convert back and forth between degrees, but this process really is not any more challenging with radians than degrees, so there's not a reason that we would have to do that conversion. So, let's take a look at how this plays out when we work with radians instead. This is telling us there is some angle who, if I take its sign, will be negative 0.98. So, if I want to find that actual value, that just means I'm going to take an inverse sign. So I've got inverse sign of negative 0.98, and I just want to solve for that term. Now, I know I'm in radians. Anytime I see pi, that tells me what unit I have. So when I'm in my calculator, I need to go ahead and change from my degree work into my radian work. So this is really important, that depending on this restriction, I change the mode in my calculator. So then I'm going to go ahead and evaluate this. Inverse sign of negative 0.98. That gives me the value of negative 1.37. So x equals negative 1.37. Now notice this one gives us a little bit of an issue because I just gave a negative angle value. I don't have any room for negatives here. But what I can do is add 2 pi. Remember, that gives me a coterminal angle. So negative 1.37 plus 2 pi is going to give me an angle that is on my circular reference frame. So I just add 2 pi, and that gives me 4.91. So we want to go ahead and graph that angle. Because I have decimal approximations here, my angle just needs to be in between 4.71 and 2 pi over here, which we said was 6.28. So I graph my initial side, and then when I come on over here, 4.71, that's a little bit far actually, it should be closer to this axis, but that's 4.71 there. So what we need to do is figure out our reference angle at that point. Oops, I'm sorry, 4.91, not 4.71. So we need to figure out our reference angle. Now we're working with decimal approximations of radians here, so I need to figure out how far do I have to go to get from 4.91 up to 6.28. So this angle value is 6.28 minus 4.91. So I can subtract that off, 6.28 minus 4.91, and we get a reference angle of 1.37. So we already have our first value, that's 4.91. Then we get our second value using this reference angle term. So up here, all of my values are positive. Over here, sine's positive. Here, tangent's positive. Here, cosine's positive. So because sine is negative, that angle value is not going to happen here where everything's positive and sine's positive over here. That means it needs to happen down here where tangent's positive. So if I start at this pi unit and go 1.37 more, that's going to give me the other value that will result in this sign. So I take 3.14 and I add 1.37. When I plug that in, I get 4.51. So my angle values are going to be 4.91 and 4.51. Then I can always go back and make sure that those two values work out. So I go to my sine, and I'm working in radians of 4.91, and I get negative 0.98. Then I go to my sine, and I take 4.51, and notice I get an also rounded negative 0.98. Now notice my decimal approximations are ever so slightly different because we did a little bit more rounding along the way, but those are both my correct final answers. So let's try two more, and again, you'll have a practice day for this tomorrow, and we'll review even more throughout the week. So if you have any questions, we'll have plenty of time to get them answered. Here, this says, given that x is in between 0 and 2 pi, identify where the cosine of x is equal to 0.12. So we know we're working in radians because we've got those pi values. Here, I'm going to take the inverse cosine of 0.12 to figure out my angle. I'm still working in radians. I get out a radian value of 1.45. So if we make our circular reference frame, we want to use our decimal approximation. So this is 0. Pi over 2 is 1.57. Pi is 3.14. 3 pi over 2 is 4.71. And then 0 will also be at the 6.28 approximation. So if I go to graph 1.45, initial side goes right here. 1.45 is kind of right up here. So that's my first angle, and notice that's the same reference value because it gets me back to my x-axis. So that's one of the values. If I go around my circle, all students take calculus. The other place where my cosine is positive, because this value is positive, is going to be down here. So to get to an angle with a reference term of 1.45, I'm just going to go down this way, 1.45. So that means I'll take 6.28 and subtract 1.45. 6.28 minus 1.45. So what I do is just subtract there, and that gives me an angle value of 4.83 radians. Those are going to be my two solutions, 1.45, 4.83. So we go ahead and plug that in. Cosine of 1.45 gives me 0.12, good to go there. Cosine of 4.83, that's going to give me 0.12 rounded as well. So both of those solutions are correct. Now, a lot of things in the real world can be identified by the behavior of sine and cosine functions graphically.